In this video, we're going to see how we can use the generated K1 and K2 to perform an encryption on an 8-bit plain text using the Simplified DES. So first, this diagram here shows you the process of encryption. The first thing here is called initial permutation. It is very similar to the permutations that you've looked at before. It is a rearranging of the bits using this sequence. After initial permutation, the bits get divided into two pieces, and a lot of functions happen on the right side here, and then the left side is brought down here, and then a swap happens, and the same function fk, which is the same as this one, happens for another time, but with using K2 in the second round. Similar to what we mentioned in the key generation video, all the information in here, which represents the functions that happen inside the f round function over here, these are all public information. So they are not secret, everybody knows what they are, and everybody knows how they function. So let's get started with this plain text. So assume this is the 8-bit plain text that we have. The first thing that we need to do on this 8-bit plain text is to apply initial permutation. So apply initial permutation, it says at the very beginning comes the bit number 2, so this bit moves here, and then comes bit number 6, so this bit moves here, and you know how the rest of this will happen. So I will go quickly and apply the initial permutation and rearrange the bits according to the values in this box. If we look here closely, we will see that we use these 4 bits to do something called expansion or expanded permutation. The expanded permutation takes 4 bits as an input and outputs 8 bits. These are the 4 bits that gets entered into the expansion permutation. So I will renumber them 1, 2, 3, 4, and I will apply expansion permutation, which rearrange them into this order: 4, 1, 2, 3, 2, 3, 4, 1, and this will be the output of the expansion. Notice that we will leave this part a little bit, and we will not touch it until we reach this step where the left 4 bits will be needed. But for now, we will leave this dark blue bits alone, and we will continue with XORing the output of the expansion with K1 that we already obtained from the previous video. So here is K1, and then we will XOR all the bits in the output of the expansion with the K1, and this will be the output. And I already divided it into 2 4-bit pieces because we take the left 4 bits and enter them into something called SBox0, which is this over here. And the right 4 bits are entered into SBox1, which is this box over here. So let's take a look on how this SBox works. First, we look at the bits in this part, and we take these 2 bits, number 1 and number 4, and we change them from binary to decimal. And this identifies which row in S0 should we be looking at. And the 2 inner bits identify which column in S0 should we be looking at. Because this is 0, 0, and 0, 0, so if we change them from binary to decimal, they will still be 0 and 0, which are these values, and the value in this matrix is 1. Notice here that the SBox takes 4 bits as input and outputs 2 bits. So these 2 bits are the number that you find in the S box, but represented in binary. So if we represent 1 in binary, it will become 0, 1, as you can see here. We will do the same thing on the right part over here. So this is row number 1. So it is row number 1. And column number 1, 1 in binary means 3 in decimal. So this looks at column number 3. The value here is 3. 3 in decimal, you change it back to binary, it becomes 1, 1. So this is the output of these two S boxes. Notice that now we only have a 4-bit output. This 4-bit output is the input for a permutation 4. This is permutation 4. So if we apply permutation 4 on this input, this becomes the output of permutation 4. Whatever you get out of permutation 4 is XORed with the left 4 bits that we didn't touch after initial permutation, which are these 4 bits. So we'll take these 4 bits over here and XOR them with this output, and then we will have the result of the XOR on the left side, and we will bring this original part, which, as you can see here in the diagram, this right side is brought over here. We will bring this original part here, and then we'll take these and swap them. So we'll take this part and swap these two, which is this swap function. I want you to remember these values because on the next slide I will start with these values swapped. So on the next slide you will find these values as 0, 1, 0, 0, 1, 0, 0, 1. Let's go. 0, 1, 0, 0, 1, 0, 0, 1. This is the output of this swap function. Notice here that you apply the same function that you applied before on the output of the swapping of the bits. So we will leave the left 4-bit part a little bit. So this part, we will leave it for now, and then we will work on this part. So I will renumber it 1, 2, 3, 4, and apply the extended permutation or the expansion over here, which is this numbering. So it takes 4 bits and outputs 8 bits. So the output of the expansion is going to be this part. Whatever comes out of the expansion gets XORed now with K2. This is the second subkey that we generated in the previous video. This is the second subkey from the previous video. We will XOR the output of the expansion with K2, and the result is going to be this, and we'll need to divide it into 2 parts. As you can see here, the left 4 bits are entered into S0, the right 4 bits are entered into S1. Do you remember how do we obtain the output of this operation? These two values are converted into decimal, and they identify the S0 row, and these two values identify the S0 column. So in this case, 0, 0 is row number 0, which is this, and column 0, 1 is column number 1, which is here, and the output is 0. 0 in decimal means 0, 0 in binary, so this is what we have over here. And then we move to the next 4-bit part. 1, 1 means 3, so we will look at row number 3, And 0, 0 means 0, so we will look at column number 0, and the value here is 2. What is the conversion of 2 from decimal to binary? 1, 0. This is how we obtain the output of the S boxes here, which are a total of 4 bits that are entered into P4, which is this part. So we apply P4 on this, and just by coincidence, it is still the same output. So trust me, again, if you apply this and you move the second bit here, and then the fourth bit here, and then the third bit here, and then the first bit, you move it here, it is still the same as the input. The output of P4 is XORed with the left part that we have been ignoring up until now, which is this part. So we bring this part down here and we XOR that, we XOR it with this part. And the output of the XOR is this. So 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, and 0 XOR 0 is 0. And then we bring the right 4 bits which we've been working on so far. We bring the original value down here. So this 1001 is the same as this 1001. And these total 8 bits are the input to the inverse of the initial permutation, which is this box. So again, you rearrange the bits using this ordering, and whatever you get then becomes your ciphertext. So finally, this value here is the ciphertext of the plain text that we started with at the beginning of this video. So now, let's assume that you already have the ciphertext and you want to decrypt it and obtain the plain text back. You can actually use the ciphertext here as the input to this whole process and do the exact same thing that we did in that video with only one change. In this step, you use K2, and in the next step, you use K1. If you do that, you will retrieve the plain text back.